going to go for the practical questions. All right, so let's get on with this. Okay, so we have gone through all of these yesterday. What's the matter? Okay, so this one is basically chapter 3. Yeah, there's a lot of um, slides. Yeah, so learning outcome, by the end of this chapter you should be able to at least see and assess efficiency of a given algorithm. Okay, number 2 is you should be able to compare the expected execution time of 2 methods given the efficiencies of each of the algorithm. That means the methods which you see the experimental, also on the efficiency of the algorithm. Okay, so this one we have gone through yesterday, just skim through very fast. Okay, this one, 2 ways to measure the efficiency of algorithm, experimental and analysis of the algorithm I mentioned earlier. Right, just skim through on that one. Where are we at? We are, is it here? Yeah, okay. I think we're here. Done this one. Okay, so we start here. So basically, if you want to, this one is analyzing the efficiency of algorithm for computing 1 plus 2 until n array, element in an array n. So for an integer n more than 0, so it is compared between the 3 algorithm that you have here, 3 algorithm for computing 1 plus 2 plus 3 and so forth of n array element. Okay, an integer n more than 0. Yeah, of course that n is more than 0. So algorithm A is this algorithm, B is this, and D is this. So this one is basically very simple. A. For basically B has a loop, but we over here we did not actually put loop in there because we want to see the simplest version, right? So if you look at here for assignment, later on if you go towards the further in the slides, there'll be these terms appearing: assignments, additions, multiplication, division, and then you come up with a total operation. This is how you basically calculate how many operations inside your source code, the program code that you are having, right? You're trying to calculate how many operations in there so that you calculate the time of execution and the response time that is given by each of the algorithm. For example, you have very simple algorithm here, A, B, and C. A is very straightforward. Sum is initialized as 0, and then you have your condition for I is equal to 1 to n. N basically is an array which you did not specify. Okay, so 1 to n, right? Sum is equivalent to sum plus I. Right, I is basically denoting the value that a user set, which comes from n. All right, so sum plus I. All right, so next one is algorithm B. I'm sure you know about this, okay, because you've done this in your assignment, not assignment, your practicals. Yeah, so this one, sum equals to 0 again, and then there is a for loop here for I equals to I 2n. Yeah, I is basically referring to values 1 to n. And then for I to I, 1 to I, sorry, for j, 1 to I, j is looking at 1 to this value. If this is 1, then 1 to 1. If this is 2, then 1 to 2. If this is 3, 1 to 3. All right, so sum equals to sum plus 1. All right, that's done with loop for algorithm B. Next one is a C. Sum equals to, this is times n plus 1, okay, divided by 2. This is just, this is also a straightforward one, okay. So algorithm C and A is quite straightforward and simple. So here, you want to, what is the number? You want to do analysis on how you find the operations which are happening in all these three algorithms. So here, assignment, you have n plus 1 for A, 1 plus n divided by, multiplied by n plus 1 divided by 2 for B. Okay? And C, basically you have only one operation assignment, one assignment, which is like this. All right? For A, you have n plus 1. Okay? All right. Next one, addition, you have n. For algorithm B, you have more complicated because you have the loop. So n multiplied by n plus 1 divided by 2. Algorithm C still maintain it 1. Multiplication, this one is come to multiplication and division is basically empty because that is a loop. So over here it says that loop for loops are not, because we just want to see a simplified version of how you come up with the total operation for this particular A, B, and C algorithm. So here total operation would be 2n plus 1. All right, n2, because you multiply that, you have n2, n squared, okay, plus n plus 1, right? 2n's multiply n squared, and then you plus with n plus 1. All right, so if you remember, we go for, whenever you're trying to denote, you want to simplify an operation for a big O, you need to remove what is insignificant there, which is the value which does not grow, which has no, what you call that, significant increase, or uh, the, yeah, significant increase in the value. It's not active. So that means whatever here, 1 and 2 are not active. You only calculate which is there, and n plus 1, which is in here. So this one will be ignored. Okay. All right. For algorithm C, you have 4 operations: sum, 2, multiply, and then plus and division. So that is 4. Very simple, right? So this one is analysis of 3 algorithms. So therefore, for algorithm A, you have total operation of 2n plus 1. Algorithm B, n squared plus n plus 1. And algorithm C, you have 4. Now you want to do analysis on this algorithm in words, how you basically put the words assignment, addition, and then total operations. Okay, how you come up to this one. Next one. So here you have total operations, total assignment, right? Plus total additions, total assignment, total addition. Okay. One assignment for initializing sum, one assignment and assignment in the loop body, this one, and an assignment addition in a for loop, an addition in for loop body. Okay, so therefore you get 1 plus n plus n. So that's 2n plus 1. So that's how you compute and get into this value. Okay, so basically you have 2n's plus 1 operations in that particular code. Next one is B. Sum is equals to 0 for I equals 1 plus n. For J, this is a loop. J equals to 1 plus I. And then you compute sum plus 1. Okay. So here it says 1j total and total equals to total plus. Right. So again, if I is 1, that means j must be between 1 to 1. Right. If I is 2, therefore your j should be between 1 to 2 and so forth. Yes. So total for 1 would be 1, and still addition would be 1, and the rest until the value reach to n value at the end, or whatever is n value at, which is your element total number of your element n. Okay. So how do you calculate your total operations? Again, you calculate that total assignments, which is referring to total assignment, and then you come for your total operation. Let's go back that one. Yeah. So total assignments plus total additions, all the additions, therefore is referring to one assignment for initializing sum, and assignment in for the loop body plus addition for the loop body. This one. Okay. So 1 plus, this one is basically 1 to n, right? Plus 1 to I, right? And then so the sum would be this computation of this both, which comes to a derivation of n squared plus n plus 1. So again, remember that you need to eliminate what is not necessary. Over here, number 1 and 2 is going to be insignificant if this basically active value keep increasing. So therefore, you find n multiplied by n, that becomes n2. Okay, and this value inside is derived outside externally in n plus 1. So that is n squared plus n plus 1. So that is for algorithm P. All right, so basically this value is increasing. It's more larger than you compare to your algorithm A, right? Because there is, if you notice, there is a squared, yeah, there on top of n. Next one. C is quite straightforward. You have sum equals to n multiplied by n plus 1 divided by 2. So you have a addition of n multiplication, and then you have division. Summation, division, multiplication. All right, so you have that. Your total operation is quite simple as well. You have total assignments plus total multiplication and total addition and total division. So all goes up to 1 plus 1 plus 1, 1 plus 1 plus 1. Okay, so that comes to 4 operations. It's very straightforward, right? This one is if you want to compare your algorithm efficiency based on graph, right? Mentioned to you that n squared is always the larger one, so it sits way on top there. That goes for algorithm B. N squared plus n operation plus 1 operation. That is here. Okay, for algorithm A, it's 2n plus 1. It sits right below this line, right? For algorithm A. Okay, for algorithm C, it's more to 1, 4. That means there's no increasing as in the squared of the value. So therefore, it is basically algorithm C is constant. All right, constant. So the number of operations required by the algorithm in F1 as a function of n. Right. So this is if you want to represent that algorithms in terms of graph. Now, how do you express your algorithm efficiency? The actual time requirement of an algorithm cannot be computed. Instead, what do? Is you find a function of the problem size. It means you identify the size of your value, okay, which is referring to, for example, n array, which has how many elements in your array, and that represents the algorithm time requirement. Because as I mentioned, as the problem size, okay, the size increases by some factor, the value of function increases by some factor and resulted in increase of the time requirement. Do you get me? If you have more functions, therefore, obviously the time to compute that particular operation increases in time as well. So you need more space, and then the more you get space, the more time you will require. All right, so that is looking at the worst case scenario. So if you want to justify that, as in you want to put it the best, that means if you still have more values, but you can perform in less time, that is the best case scenario. Okay, so basically, how you want to increase, how do you want to see all this in terms of symbols, notations, they call it. So you want to represent that. Computer scientists basically use the big O notation to represent an algorithm efficiency or complexity. There are many uh, O notations. So this one, it says here, these are the steps to derive the big O notation for an algorithm. Okay. This one, there's a question, if you notice in your practical 3, yeah, self-review, practical 3, uh, please list down or describe the steps to derive the big O notation for an algorithm. So if you notice, we go back to our video on a big O notation, right? So we go back to that video on our big O notation. In order to come up with a big O notation value, like at the end of that, how you compute to become O of n, O of 1, okay, all those things, notation. So first thing, you have to use the given identities and ignore smaller terms in growth rate function. So I mentioned, right, all these details is important because that's how you derive this value, this particular notation. Okay, for example, here, if the growth rate function is 4n squared plus 50n minus 10, now that is computed as this way, O notation. O notation, inside you put that 4n squared plus 50n minus 10. And then you derive that. You want to ignore smaller terms in growth rate function. Which of that basically has a active growth rate function? So over here, like it says, you use the given identities, all these identities are given, ignore smaller terms in growth rate function. So most active, as you refer to previous example, for example, in the video that we have, all right, 4n would be the most potential in the growth rate function. So therefore, you ignore all these details, right? All these details you ignore. So you take this value, all right? Therefore, how you present that is that you put O notation of 4n squared, all right? And then again, you come up with this, you identify this identity of the value which has the active growth rate function. And then what will happen is that you want to ignore the smaller terms. Now you remove the smaller term just like how you remove here. Therefore, over here, then you remove 4 because as the growth rate increases, this value no longer significant. Therefore, you put it, derive it as O n squared by ignoring the constant multiplier, which is 4, okay, or coefficient. So basically, this function you will derive until, oops, sorry about that. Here, this is the end of your big O notation derivation for this question. First you do this, and then you put in the simpler version, and then you put, again, you keep doing this particular steps, and then you reach to the end, which is this one. Oh, you must remember, whenever you want to derive big O notation, smaller terms should be ignored, because as you process, you only are going to see what is the bigger growth rate function, which is this. Therefore, everything comes to, at the end of it, whether on or n squared, depending on what you have here. Okay, so this is the n value, what you have for that question. Next. So this one, I put it down so you can basically imagine and visualize, right? What are the steps in detail on how you derive big O notation to an algorithm. So here, these are the main point, right? But how do you get that? What is the, how do you put it into words? Break your algorithm function into individual operations. Individual operations, as in, remember a while ago we have that ABC, like this. Yes, break that into individual operations, okay? Right. Like this, okay? And then okay, where's this? Calculate the big O of each operation, right? Add up the big O of each operation together. Remove the constants, which are the numbers. Find the highest order term, and then that will be what you call the big O of your algorithm, as in here. Okay, so you have this value at first. You find out about what you have, how many assignments or operations you have in your source code, and then you put that into this. And then after that, you start to basically get O in action by putting it into this kind of derivation. Therefore, you eliminate what is insignificant, which is constant, and therefore you identify the positive growth rate function of this and put it into this bracket, because this is how you represent O notation. So therefore, and again, over here you have to eliminate the constant multiply. Okay, so that is how you got that big O notation. All right, so look at this graph. Whenever you get this value on your big O n squared, that arrow will always go like this. It looks like this. For your O of n, O of n, O on order of n, okay, the order of n, O of n, sorry, and then O of log n, okay, that will go like this. Your O of n will look like that, and then O of 1 will look like that. That is basically 1 inside is always represent that the value is constant. Okay, so this is your time which you require in response to your input size. All right, so this is a point to step or steps to derive big O notation in an algorithm. Now these are the notations what you have in big O notation, right? Like these are the notation and the type. What are the type for all this? I put here so that you can actually visualize what is it all about. Because sometimes when you refer to all the slides, it is quite confusing. It's all jumbled up, because that is to actually give a point of view of someone who is already an expert in big O notation. For someone who is just getting used to a beginner, it is good to actually have this big O notation to put in here. And then you know what exactly it means, right? 0, 1, the type is constant. Like I said, 1 is always constant, or that value 2, 3, and 4, that is constant. O log n, logarithmic, logarithmic, so that is representing log and a logarithm, yeah. And then O more than N, O of more than N, that's sublinear, but we seldom see O more than N. Okay, we always see O of 1, O of log N, O of N. Okay, that is representing a linear function. Yeah, linear means one after another. And then you have this as well, N of log N. That is basically done under, okay, as you see here, that is a hash. This one will go binary search of a sorted table. This one sublinear using a parallel processing, but we seldom do that. Of N linear as well. All right, so finding an item in the unsorted list. So basically, in your ADTs, you have all those lists, stacks, queues. Everything is basically using a different notation to where you're trying to calculate the operation inside your code. So that's why it says here examples are such that this basically represents presented in this particular situation. Okay, O n square. That quadratic, okay, type is quadratic. Quadratic means what? Quadratic means if you have sorting loop and all that, yeah, for this equals to this, those four loops, those are quadratic. Whenever you have a sorting, you want to go into a loop that is using this quadratic, yeah. And this exponential, it's we don't usually see this, but that is basically as your value increases exponentially, so you add that c into n, right? So that is seldom being used. Increase based on the exponent of a constant c. So these are the description of all this notation. Okay, and then this one as well we don't use as much. It's not n, O of not n. Okay, it's a factorial. Factor means it's keep increasing. Factor by factor increases in proportion to the product of all numbers included. Yeah, so you multiply and then you keep increasing. Factorial. Right, so that is in brief about big O notation. I think this should help you to actually know, right? This is exercise 3.1. Derive big O notation for algorithm A, B, and C. Right? So you have the growth rate function for A, B, and C a while ago. Now, how do you do that? You have 2n plus 1. Again, whenever you see here, the second step is to remove what is insignificant, which is looking at constant values 2 and 1. Therefore, what do you have? Your big O notation will be O of n, right? For algorithm B, that is the end result. Algorithm B, n squared plus n plus 1. Again, you have to remove the insignificant constant value 1. All right, therefore, what do you have here? Since you have uh, 1n squared, you pick n squared and n. Which one of these are actually a has the higher growth rate function? Therefore, you selected n squared. So therefore, your end result will be O of n squared, right? For C, you have four operations altogether. Basically, this denotes nothing. You don't have any factor or you don't have anything that increases it or makes it increase as time goes by because you only have four operations. That's it. What do you do here? You remove that and then you basically translate that into constant 1. Therefore, you put it O of 1. This O notation, big O notation, represents what? That the value is constant. All right, where is that? Yeah, yeah, this one. Okay, so basically remains constant regardless of the size of the data set, right? That is in your graph, which is here. Okay, right. Okay, so this one I already mentioned, yes. Mm, yeah, okay. So This one is big O notation.
Big O notation, a way to describe how well an algorithm performs as its input size grows. As we add more inputs or data points to an algorithm, there are two things that might grow in complexity. It may take longer to run the algorithm, which we call time complexity, or it may require more memory, which we call space complexity. The variable n represents the number of inputs. Now imagine n being scaled up to infinity. The faster the result grows after each step, the worse your algorithm performs. In technical interviews, you'll often be asked to estimate the time or space complexity of the code you've implemented. Take, for example, a loop over an array of elements. It takes exactly 1 unit of time to loop over each element. This is known as linear complexity, because we have a perfect one-to-one relationship between the number of inputs and the amount of time it takes to execute the algorithm. But we can often do better than linear time. If we have a sorted array, we can implement a binary search, where we start in the middle and then jump back and forth until we find the actual value we're looking for. This is known as logarithmic complexity, and it scales much better to a large number of inputs. At the most efficient end of the spectrum, we have is looking up an element in an array by its index. No matter how big that array is, it should always take the same amount of time. But things can also get less efficient. Imagine a loop within a loop. This is quadratic complexity, where the number of inputs is raised to the power of 2. And things can still get worse with exponential complexity. Imagine looping over every possible combination in an array. Some algorithms may have multiple different growth rates of complexity. Always simplify your notation down to the fastest growing, worst case scenario. This has been Big O Notation in 100 seconds. Thanks for watching, and I will see you in the next.
Okay, that's just a brief explanation of what big O notation is. I have already explained that, right? So just to recap back to get you remember again. So how do you see big O notation, verbalizing it? To say algorithm A has a worst case time requirement proportional to n, so we say what? We say A is O of n, or you read it as big O of n. This is how you read O of n, big O of n. Okay, for the other two algorithm, algorithm B is O of n squared, C is O of 1. Okay, that is constant. Now, next one is the seven most common functions in algorithm analysis. These are the 7 common functions. Yeah, so this is a 7 important function for algorithm. Number 1, constant function. This is the simplest function. You have n equals to c. Okay, this one I actually took it from a note in some website where it gives you elaboration and explanation. Okay, so I'm going to just go and skim through very quickly, right? 1 is constant function. The simplest function would be f of n equals c. That is some fixed constant. All right, so value of n over here, it doesn't matter. It can, example, adding 2 numbers, assigning variable, comparing 2 numbers. So that is constant function, right? And number 2 is the logarithm function, fn equals to log bn. Here it says that for some constant b more than 1, this function is defined as x log b, and if and only if b is x equals to n. So basically that is how they define for logarithm function in algorithm analysis. Next one is the linear function. This linear one after another arises mainly when we have to do a single operation for each of n element. So iterating through an array of size n, etc. So you use that linear function. N minus log minus n function, that is n log n. So these basic function to assign an input n in the value, and the value of n times the log base 2 of n. Okay, so a lot faster than quadratic if we can improve quadratic to n log n. Quadratic functions, you have this one. We don't normally use this, but it is good to know. Arises mainly in algorithm analysis because many algorithms have nested loops. So therefore you have representing the inner loop performs linear number of operations. The inner loop performs linear number of operations as well. Okay, so that is in quadratic function. So anyway, next one. For cubic function and polynomial, you use this. We don't normally use that, but this is good to know as well. Last one is exponential function. Fn equals to Bn, right? So for instance, we have a loop that starts by performing one operation and then doubles. So you use this representation, right? So I need you to read on that one, yeah? So this one is just the explanation of what has been given a while ago. Fn equals to C. Now it says where C is a fixed constant, C equals to 5, C equals to 2 to the power of 10. Okay, right, read on this one. I mentioned this already. And then this one is again Fn equals to log Pn, right? This is, I mentioned this already. This, I put this translation here so you can understand. Log B, and if and only if B is power of x equals n. So what is that? Read on this one, yeah, where x more than 0, it should not be more than or equals to 1, right? X more than 0, B more than 0, and B is not equals to 1. So the base can be any positive number except for 1. Linear function is this. Next one is the log and log function. Yeah, so this is basically used inside a loop. So next one, another one is with the nested loop of n squared. Okay, cubic function is this one. Okay, so this is denotes n cubic. All right, Fn Bn, where B is a positive constant called the base, argument n is the exponential value. Yeah, read on that one. Yeah, this for your information. This is your growth rate function, as in n log n log n log n log n and log n square and what so forth here. So those are the typical growth rate function evaluated as increasing values of n. Right? So your base logarithms are base 2. This was just to show you how it increases according to what n value is. Right? So this one, again, is O log n. How it increases if the value increases, what are the number of digits, and what is this log n value, basically referring to this one. The number of digits in an integer n compared with an integer portion of log n, log 10. Now this one is the algorithm and O of n algorithm representation in a diagram. So for I equals to 1 to n, therefore sum equals sum plus I. So whenever you define I, sum equals sum plus I. If I is 1, if I is 2, therefore you say 1 to 2, right? So here an operation is 1, 2, 3, 4 until n. So basically keep increasing until you reach n, O of n, right? So this is picturing for O of n. Next one is O of n squared. So this one is the definition or operation that you can derive for O n squared. Okay, so big annotation would be inside here is the number of elements you have in an array until n element. So therefore, to actually sum that up, you represent that by using O n squared. Okay, so I is equal to 1, I is equal to 2, I is equal to 3, and I n, meaning value of n. Right, so this is just how you picture in terms of efficiency. The more number of values, the more work you are doing, basically looking at this. Okay, so this one is another one. For I equals to 1 plus 1 to n, similar for j is loop equals to 1 to n sum plus 1. So similar to this, you have the O notation, n values multiply n values. So how do you actually sum them up? You put it into O n square. All right, so that is just simple as that. Okay, so growth rate functions for n size of problems, and then this one is growth rate function for 2n problems. When it effect on time requirement will be these results. So for this one, it says, like for example, yeah, just to say this briefly, one, the growth size, the size of n is 1, and therefore obviously your size uh, for 2n problems is 1, and there is no effect because you don't do any much of operation there. N log n, 1 plus log n, remove your 1, that becomes log n, and basically doesn't cost much of time to actually compute or operation, so it's negligible. N to n, basically your n doubles over here, and therefore your effect on time requirement will be double as well, until what you reach when this value increases, this one as well, growth rate function for size 2n problems increases, and that is what your effect on time requirement will be. Okay, so this one is basically looking at your picturing efficiency based on the function g of these operation or values. The time to process 1 million items by algorithm of various orders at the rate of 1 million. Okay, so this one is just a notation definition. I think I delete that. Okay. This one also you can read, yeah. Read on that one. Okay. Comments on efficiency. A programmer can use O n squared, O n cubed, or O n, or 2 of n, or okay, as long as the problem size is small. At a 1 million operation per second, it would take 1 second. For a problem size of 1000 with O n square. For a problem size of 100 with O n cubed. For a problem size of 20 with O 2n. Okay, so that is a comment how you actually say that. All right. So this one is identify the big O notation in the following method. What do you do is you come up with all these solutions, okay, by looking at this one by one, and then this is the end result. The code traverses through each array element to concatenate its value to the string variable string. Yeah, so and then this is the end value for this particular question. And then you have another, this is just like review question. Using big O notation, indicate the time efficiency for the worst case of each task below. Okay, state your assumptions, if any. All right, so using big O notation, what will this be? Okay, whether it is O of 1, constant, or of n square, okay? All right, now let's see. A, after arriving at the party, you shake hands with each person there. What is this? Which one of that big O notation can you get there to be represented at?
Big O N.
Oops. Yes. Next one. Each person in the room shakes hand with everyone else in the room. Which one?
N square.
Each person in the room shakes hand with everyone else in the room. Yeah. O of n squared. Because each person, first thing, you shake hand with everybody. Then each of those people in there, that means a double, okay, will do the shake hands with everyone else in the room. Therefore, O of n squared. Now you climb a flight of stairs. What is that? O of n. You are doing it, one person. And you're sliding down the banister still, O of n. Okay, that's not O H, O of n. After entering an elevator, you press a button to choose a floor. That is constant. You choose means you get one operation. You ride the elevator from ground floor up to the nth floor. Therefore, of n. You read a book twice, of n. Right? So these are using big O notation indicate the time efficiency for the worst case of each task below. These are your assumptions, yeah? Now register your references. Okay, so that is your learning outcome. Okay, done with that. Any question? It's just very a lot of reading to be done here, but I think if you look at the example of the video which I've shown you yesterday, it is quite clear on how you should be able to do that into deriving all this notation. Yes. Okay, so let's now. Any question?
No.
Okay, so let's get on to our topic for today, which is your practical. Okay, we hang on. Where are we at? Now we are at week 3, right? Week 3. So basically, our lecture would be efficiency of algorithm, right? Efficiency of algorithm, and then also some array-based implementation of ADTs that will be in your practical. So practical, still under efficiency of algorithm and array-based implementation of ADTs, which is your stack, your list, your queues, which you are doing in your practical. And then I will be giving you a bit of sample source code for you to get on with your practical. Okay, so just to give an overview of what you should be doing here. For next week we're doing this array-based implementation of ADTs, still continuing. Yes, for your practical lecture as well. And then you continue on array-based implementation as well. All right, let's look at the question. All right, see this one? This is your pre-practical class submission. Again, I am not sure whether you should do this double time or what you should do this on your own. I will inquire, okay, because I have already gotten you guys involved with your practical questions, which are the codings, right? This one is more to a practical meaning based on your lecture, right? So you should be able to actually answer this question. What is the big O notation, number 1? And number 2 is to describe the steps to derive the big O notation for an algorithm. Okay, so all is in your note with examples. All right, next one. Let's see the practical question right now. So here, last week, the week previous week, right? You have gone through a list applications done 1, 2, yeah, until that, right? 1, 2, 1, 2. Yes, done. Next one is stack application. This one, yeah, you did this last week, yes? 3 and 4.
Yeah.
Okay. Yes, 3 and 4.
Yeah.
Yeah. Okay, now we go for, and then you also, okay, now you have queue applications. Basically, all these questions under this is the ADT applications, right? So another one question is queue application. Last week was stacks and lists. Now is queue. And then you have 5, 6. 5 is easy, palindrome. It's a very simple, straightforward how you actually display whether or not this it is if you input a word, for example, word, and then it should be able to tell you whether it is a string, whether the string is a palindrome or not. Okay, based on uh, your logic assignment of your algorithm. Okay, so this one, your result would be to determine whether a string is palindrome or not by inserting certain words. Okay. So that is number 5. You can do that. Number 5. Have you done the palindrome class?
Yeah.
You've done palindrome, right?
Yeah.
Yeah. Okay. So move on. 6. This one I'll give you. I think I give you this one. Did I? Chapter on the beans. Post office. Not yet.
No. Wait.
Not yet. Not yet, right? I think post office. Let me see your class. Hang on, yeah. Whether I give you that post office. Practical materials. Did I give a code? Question. Oh, I think I didn't. I haven't given you the code, right? What week 1, week 2, practical materials.
Oh yeah, got it.
Yeah, I have it. So hang on, post office sim, right? Is the question. Customer.java, post office sim.java. Yeah, so you should have this and this in your box. Let's see the customer.java and then post office sim. Okay, so you got that code, right? Should be able to attempt that question. Right. Okay, so now you can start with number 6. You haven't attempted 6, right? You only do until 5, right? C5.
Oh yeah.
Until 4.
Yeah.
I mean.
So can attempt this number 6. 6. Yes, 6A, B, and C. Okay, 6A, B, and C.
Okay.
Practical to abstract data types. You should be actually done doing this one. Efficiency of algorithm. Okay, never mind. Actually, you're supposed to actually do this one as well, efficiency of algorithm. But if I were to look at your coursework, course plan, number 3, yes, your practical should have touched on efficiency of algorithm. Okay. Okay, never mind. What you do is, this one have not been done, right? Number 6. Q. Q operation. If you, yeah, you can do 6, C6, C6, right? C6. Yeah, C6. And then complete this. This one basically all the tasks for post office sim. Yes, A, B, and C. The event handling for the take number button, the text area about button is that you can display your number with the automatically generated next sequence number. So you have a number over here. So when you will be assigned to, if this number, the last number, is already done, then your number, this one will go and assign to each of the counter, in any one of the counter which is available, for example. Yeah, see? The event handler for the take a number button, the text area below this button should then display a number with the automatically generated next sequence number. B. Counter listeners action perform method. To be executed when any of the counter and buttons are clicked, ensure that the text field in the first row under the customer user interface section, yeah, will list the next number to be serviced here. Okay, so that goes to under user interface, customer user interface. All the remaining text field below the top row will be updated accordingly. Yeah, okay. So this is counter 1, counter 2, counter 3, counter 4. Your number is 1007. If this particular counter has already completed task, therefore next number in line will be 4, 3, 2, 1. Maybe your number 4, your 7 maybe, right? Unless if there is a number 6 here. Okay, so it should be able to generate that those numbers will keep changing if one number is out. All the remaining text field below the top row will be updated accordingly. Okay, so everything will be able to be updated once the one number is. Hang on a second, I got something on. Hang on a sec, be right back. Okay, now let's go back here. Okay, counterlessness action performed. Yep, that's done. All the remaining text field below to top row will be updated accordingly. Announce the sequence number to be serviced and the count number to go to. Yes. Okay, next one. Next one is very easy. I think you should be able to do this. This is event handler for print analysis button. That means this one. Okay, to be executed when it's clicked. So your figure 1.4 is basically referring to your expected output of what should be printed. All right, so this one is your printer. This is your printed report, analysis report. Okay, done with that. Here is practical number 2, just briefly to show you what we have in the practical 2 abstract data types. Number 1, A, rational function form A or B, where A and B are integers and B is not equals to 0. Write in additive specs to represent fraction. Include operation to set and get the numerator and denominator, as well as perform arithmetic operation. Okay, all right, never mind. This one we don't do first. This one we ignore. And now I want you to complete this one. Yeah, I want you to complete this Q. And then after that, this one we don't do first. This one is basically infix, prefix, and postfix. Remember that? Yeah, so this we don't do yet. We'll get back to this one later on. But yeah, right. Now we go into this efficiency of algorithm. We want to do one of the program for Java efficiency of algorithm. Question number 1 only. Yes. All right, so I want you guys to try and attempt this question here. Q. Okay. And then done with that, we're gonna postpone on this one, abstract data types, because on top is already abstract data type, right? What is this? This is a application. Oh, application of ADTs. Hang on. Let's see your this tree of algorithm application. Yeah, application, right? Applications be under this. Yes, and then here is a bit of the array-based implementation of ADTs and efficiency of algorithm. Okay, this application. So we do abstract data types. No, we don't do that. Okay, we do this one. This one, efficiency of algorithm. Okay, class. So you do part C. This one, right? C. C A B C. 6 A B C. 6C 6 A B C. And then you go straight to this one, practical 3, which is efficiency on algorithm. All right, so what's this? It says, write a Java program that implements the 3 algorithms in chapter 3. Remember that? You have algorithm A, B, and C, and records their average execution time based on 10 iterations for various values of n. Example, 10, 100, and 1000. So the program should display a table of the running times of each algorithm of various values of n. Okay, now let me show you. Let's get back to that question. Yeah, right, this one here. Yeah, okay. I think this is the one. Okay, let's get back to that algorithm first. Here. Analyzing the efficiency of algorithm for computing 1 plus 2 plus until n. N is not known. What is your elements, the last element or the total element of n? Okay, for an integer n more than 0. Okay, so you have algorithm A, B, and C. Your question is, you need to see this one. You want to see this. Okay, so how can it get value? What are the value that you can compute for all these 3 assigned algorithm based on this value? Okay, so basically your code will involve that you add all these values into your uh, assignments of your code operations. Yeah, so this one involves in there. All right, assignments for algorithm A would be n plus 1. Algorithm B would be 1 plus n plus 1 divided by 2. Okay, algorithm C would be only 1 constant value. Addition, okay, n, algorithm B n divided by n plus 1 divided multiplied by n plus 1 divided by 2. Algorithm C will be n value 1. And then, so what do you have for multiplication? You should justify here. And the value for C, of course, remain constant all the way because that is, after all, a constant value. So your total operation would be 2n plus 1. And this one, your operation for algorithm B will be n to n squared plus n plus 1. Okay, so you should involve all this operation in your code. Now algorithm C would be 4. Okay, so hang on, let me see whether I have a second. A sec, let me search some file. Okay, never mind. Let me search a file for this particular question 3. In the meantime, you can start attempting that question. This one, yeah. This Q. This. Okay, 6. All right, so you just do this one for the time being. I will search for file which is related to question 3. Okay, this one. Okay, class, you may proceed with that one. I'll search for the document. Okay.